So what's different on this side? So when I press, if I lift that object with some effort force over here, is this move more or less than my hand? Okay, it's gonna move less, kind of depending on where my fulcrum is here, right? So here's the way of thinking about this. Energy will be the same. The energy I put in is the energy I get out. And that energy is a force times the energy I'm putting in is the work I put in, force times the distance. So this force times distance will equal this load times some distance. Okay? So that means that if you think about that, I can lift that load with a smaller force that's much smaller than that load. Because the force times the distance will be the same on both sides. So let's go through that. If I apply some force here, let's say that this goes down 2 feet. It's going to lift this 1 foot. Okay? If the energy is the same on both sides of this fulcrum, that means this load is twice the amount of force I put in. Okay? So I think you can see. I think what's easy to see here is the distance amplification, or you're moving farther on this side than that side. That's easy to see. But part of what you also want to think about is that your force times that distance, that longer distance, is a certain amount of work that you're applying to that load. Okay? And that allows you to lift a much larger load, but a shorter distance. Okay? Now, levers can be used in a couple of different ways. You can also use them like this. This is actually more, what's an example, what's a pretty common, can you think of a common example of a lever? So this is a lever that's used it's kind of the same idea, but you put in the fulcrum, both the load and the effort are on the same side as the fulcrum.
Wheelbarrow.
Yeah, wheelbarrow is a pretty common example. Your pivot is all the way over, your effort's all the way out here, and your load's in between. Okay? So again, your effort force is moving a long distance, your load's moving a shorter distance. But you're amplifying, the force you apply here is being amplified essentially by the ratio of the distance from the fulcrum. There's the distance from the fulcrum to your effort, the distance from your fulcrum to the load, and that's the amount that you're amplifying. That's your mechanical advantage. So really the most efficient way to make, if you wanted to lift the most weight possible with a certain force, where would you put the load?
Closer to the fulcrum?
Right. And what would be that one? So if you put it all the way down here, you could lift a lot of weight, but
There's friction.
well, there's friction, but what do you lose so you're cranking up that mechanical advantage, but what are you losing in that case?
The distance.
Yeah, the distance, exactly. You can't move it as far. You can move it a little bit, but if you just need to, it's like whenever you have a crowbar and you just want to move a rock a little bit, you could crank way out on that fulcrum and move it a tiny bit. You amplify your force a lot, but you're only moving a small distance. So it's the main message here, one of the messages here, is you got to think about that force times distance idea. That's how this amplification happens. When you're amplifying your force a lot with a simple machine, chances are on the load side, you're not moving as far as the effort distance. So here's another, this is what we were talking, this is the simple machine that the folks that made the launching machines created. So there's actually a terminology for these. This is a lever of it. There's 3 classes of lever. This is I think they're called classes. This is a class 1 lever. This is a class 2 lever. And this is a class 3 lever. The class 3 lever is actually doing exactly the opposite. So this is what your launching machine did. Your launching machine, well, actually, your effort force was over here. I kind of messed this up. but you're putting the fulcrum closer to the effort force than to the load. So what would this be? What would we use this for?
Tongs or tweezers.
Yeah.
Oh, tongs or tweezers. Actually, that's an interesting idea. Right. Yeah. So you're actually, that's interesting, tongs and tweezers. Because you're actually lowering the amount of force that you, so the force you're applying here is actually less than is being applied in the load. The advantage you're getting, what's the advantage? What's the point of this kind of lever? It goes farther. All right? Or you're amplifying distance or you're amplifying velocity. So, what's that?
The load.
Well, if you have your hand here, all right, this is the effort is where your hand is, right? If you move this a certain distance, this moves farther, right? Right? So you're using it as a catapult. Your force is being applied here. That's amplifying the motion. It's not amplifying the force, it's amplifying the motion.
What about like a pen or a fork? Would that be like a pen or a fork?
A pen or a fork.
If you're like holding it like this,
Because you're amplifying distance. I see what you
I'm
mean.
holding it in the
I see what you
middle.
mean.
The load is, if this were a fork, the
I see what you
load
mean.
is right here. I'm putting my force in the middle.
Well, I mean, one way in which you're right. Well, but I mean, I think what you're describing, so if you do, so here I'm pivoting around some fulcrum really close to my hand. And what I'm doing is I'm really amplifying the motion of my fingers, right? So down here, the motion's getting, the motion, yeah, so actually chopsticks is maybe an even better example, because a little bit of motion's getting amplified a lot at the end. So that's kind of what the point of this third class of lever is motion amplification instead of force amplification. So you're actually losing on the force side. Does that make sense?
Yeah.
Sort of? Yeah.
But you would hold it like
Oh,
Tweezers.
yeah, tweezers.
What else you got in your bag?
So,
So
where's the folk? Here?
The fulcrum's right here.
Okay.
I mean, this is a
And
little
low
different
force.
because this has actually got a spring involved too, right? There's
So is that like two third-class levers together, working together?
yeah. I mean, it kind of depends on what the load is here. So if you're holding something heavy, I think it's a little more complicated. I mean, tweezers. I mean, you'll have to think about this. This is your homework problem. Figure out what this is. No, I mean the tweezer's a little more complicated because you've got a spring holding two. You've got two levers that are held together with a spring. All right, what else we got here? So this is a wheel and axle. So here's another case, like in the case of like a well. Okay, when you're drawing water from a well, there's actually a machine that gives you a mechanical advantage in that case. All right? So you have some load. This is your water bucket. You're pulling up your water bucket. There's a certain amount of force pulling that down. If you just pull it up with your hands, you're going to have to apply the same amount of force. The force you pull up will be equal to the weight of that bucket of water. But if you use a simple machine, a wheel and axle, where you have an effort that's way out here on the outside of the wheel, and you're pulling up on an axle that's smaller. This has to do with the ratio of the radii. Okay, so you're pulling out at this radius. The string's being pulled up with that smaller radius. Okay. Now you can see just by looking at this picture, if you go one circumference, if you do this one time, your hand's going through a certain distance, right? The bucket's going to come up more or less than that distance.
less.
A lot less, right? Okay. But is the force you're going to be applying more or less than the weight of that water? A lot less. less. So you're moving much farther. You're having to do that much longer distance, but you're applying a much lower force. Okay? Again, the force and distance are going to, force times distance will be the same. Your force times your distance will equal this force times its distance. But the distance is much lower here, and the force is much higher on the load side. So you're getting a bunch of mechanical advantage. You're going through a much larger distance, but you're having to apply a much lower force. And it turns out the mechanical advantage on this machine is simply this radius over this radius. Okay? I mean, is it? No, what's your question? This is more fun.
Yeah, I like bringing here.
No, not at all. That's not true. I'm sure that's not true.
Let's see if she's down.
Okay, you saying, okay, the amount of force, the energy, I'm thinking energy, I'm translating the energy as for you to pull that bucket and say,
Okay.
well, it's the same amount of energy it's gonna take to lift it up, correct?
The energy, so force and energy, we got to make sure that
Okay.
they're two different things.
Right.
Okay.
I got those, but my question is, doesn't it also depends on the, doesn't it also depends on the mass of that object?
Absolutely.
So even when we went back and talked about
Let's go back.
the levers, wouldn't it also depends on how heavy the object is?
Absolutely.
Okay.
So the question is, so for a given, let's say this is 100 pounds. Okay. This is 100 pounds. So you all know on a balance, if we have a seesaw and this fulcrum's right in the middle, to balance that seesaw, if I have 100 pounds here, I would need 100 pounds on the other side if this fulcrum were right in the middle, right? To balance this, if I have 100 pounds here, I might just have to put 25 pounds here. And that will even this out. Okay? But I think the other question you had was about energy and force. Again, you want to think about these. Okay, so there's three words that we're talking about today that we have to get straight. Work. Okay, there's force, which I think we've worked a lot on. Force, we've worked a lot on what that concept means. There's energy. We've worked a lot on what that means. Energy means a lot of different things. There's potential. Let's just talk about potential energy, gravitational potential energy. Let's just talk about that kind of energy, because that's what's happening in all of these simple machines are lifted. Almost all of these are lifting something, right? That's what they're doing. They're lifting something out. From what examples I've given you.